Not all motors can be safely driven off of a frequency drive. AC induction motors and synchronous motors are typically compatible with frequency drives. DC motors and stepper motors are not. The motor's rated frequency should match or exceed the operating frequency of the frequency drive. The drive's output voltage should match the motor's rated voltage. Motors designed for fixed frequency operation may require additional cooling at lower frequencies. Ensure adequate ventilation or use motors specifically designed for variable frequency operation. Consider the motor's torque speed characteristics at low frequencies. Some motors may experience torque drop-off or resonance at very low frequencies. Running a motor at a low frequency for extended periods can potentially have the following effects. Firstly, increase motor losses. Lower frequencies result in higher magnetic losses in the motor, which can lead to overheating. Secondly, higher stator currents. The motor's stator currents increase at lower frequencies, which can overload the windings. Thirdly, torque pulsations. Motors operated at lower frequencies may exhibit torque pulsations, which can cause vibration and stress on the motor and load. Fourthly, bearing degradation. Low frequency operation can reduce the lubrication effectiveness of bearings, leading to premature wear. For mitigation strategies: 1. Use motors specifically designed for variable frequency operation or low frequency applications. 2. Employ proper cooling measures to prevent overheating. 3. Select drives with output filters to minimize harmonic distortion and stator current peaks. 4. Avoid operating motors at excessively low frequencies for prolonged periods. 5. Monitor motor temperature and vibrations during low-frequency operation to ensure safe operation. When selecting a motor to be controlled by a variable frequency drive, also called a VFD, several factors must be considered to ensure compatibility and optimal performance. Firstly, motor type is critical. AC induction motors are the most common and generally well suited for VFD control. Synchronous motors can also be used effectively. However, DC motors and stepper motors are not compatible with standard VFD designed for AC motors. Secondly, the motor's voltage rating must align with the output voltage capabilities of the VFD. Ensure the VFD can supply the required voltage to the motor to achieve its rated performance. A mismatch can lead to reduced performance or motor damage. Thirdly, the motor's rated frequency, typically 50 or 60 Hz, should be considered in relation to the VFD operating frequency range. While VFD can operate motors at frequencies above and below the rated frequency, sustained operation at extreme frequencies can impact motor performance and longevity. Fourthly, cooling is an important aspect, especially when operating motors at lower frequencies. Standard induction motors often rely on an integral fan coupled to the motor shaft for cooling. At low speeds, the fan's effectiveness is reduced, potentially leading to overheating. Motors designed for VFD operation often include auxiliary cooling systems such as separately powered fans to ensure adequate cooling regardless of motor speed. Fifthly, insulation is another key factor. VFD produce voltage pulses with rapid rise times, which can stress the motor's insulation. Inverted duty motors are specifically designed with enhanced insulation to withstand these voltage stresses, preventing premature insulation failure. Sixthly, the motor's torque characteristics must be considered, particularly at low speeds. Some motors may exhibit reduced torque capability at low frequencies, which can affect their ability to start and drive loads effectively. Motors designed for VFD operation are often optimized for constant torque performance across a wide speed range. Seventhly, encoder feedback may be necessary for applications requiring precise speed control or positioning. Encoders provide feedback to the VFD, allowing it to accurately regulate motor speed and position. Eighthly, harmonic filters can be used to mitigate harmonic distortion produced by VFD. These filters reduce the impact of harmonics on the motor and the power system, improving overall system efficiency and reducing the risk of equipment damage. Ninthly, proper grounding is crucial for minimizing electrical noise and ensuring safe operation. Follow recommended grounding practices to prevent ground loops and reduce the risk of electrical shock. Tenthly, motor size should be appropriately selected for the application. Oversizing the motor can lead to reduced efficiency and increased costs, while undersizing can result in overheating and premature failure. When considering the operation of induction motors, the relationship between voltage, frequency, and magnetic flux is fundamental to understanding motor performance, especially when controlled by variable frequency drives. The voltage-to-frequency ratio, often expressed as volts per hertz, is a critical parameter that must be maintained to ensure proper motor operation. In an ideal scenario, the magnetic flux in the motor should remain constant to maintain consistent torque capability. The magnetic flux is directly proportional to the voltage and inversely proportional to the frequency. Therefore, if the frequency is decreased, the voltage must also be decreased proportionally to maintain a constant volts per hertz ratio. For instance, if the motor is designed to operate at 480 volts and 60 Hz, the volts per hertz ratio is 8 volts per hertz. If the frequency is reduced to 30 Hz, the voltage should be reduced to 240 volts to maintain the same 8 volts per hertz ratio. Failing to maintain this ratio can lead to either overfluxing or underfluxing of the motor. Overfluxing occurs when the voltage is too high for a given frequency. This can saturate the motor's magnetic core, leading to increased magnetizing current, higher core losses, and potentially overheating. The motor may also produce excessive noise and vibration. Underfluxing, on the other hand, occurs when the voltage is too low for a given frequency. This reduces the magnetic flux in the motor, which decreases the motor's torque capability. The motor may struggle to start or maintain speed under load, leading to poor performance and potential stalling. Variable frequency drives are designed to automatically adjust the voltage to maintain a constant volts per hertz ratio over a wide range of frequencies. However, it's essential to configure the VFD correctly to match the motor's specifications. Some VFD offer different volts per hertz patterns to optimize motor performance for specific applications. For example, a linear volts per hertz pattern maintains a constant ratio across the entire frequency range. A quadratic volts per hertz pattern reduces the voltage more rapidly at lower frequencies to improve low-speed performance and reduce core losses. A multi-point volts per hertz pattern allows for custom voltage settings at different frequencies to fine-tune motor performance. At very low frequencies, additional considerations are necessary. Standard induction motors rely on a shaft-mounted fan for cooling, which becomes less effective at low speeds. Therefore, the motor may require additional cooling, such as a separately powered fan, to prevent overheating. Furthermore, the volts per hertz ratio may need to be adjusted at low frequencies to compensate for the motor's inherent characteristics. Some VFD offer a boost function that increases the voltage at low frequencies to improve starting torque. However, it's important to avoid overfluxing the motor, as this can lead to overheating and damage. In summary, maintaining the correct voltage to frequency ratio is crucial for proper motor operation when using a variable frequency drive. The VFD should be configured to match the motor's specifications, and additional cooling and adjustments may be necessary at low frequencies to ensure optimal performance and prevent damage. Variable frequency drives offer several control methods to optimize motor performance for specific applications. These control methods vary in complexity and performance characteristics, allowing for precise adjustment of motor speed and torque. Firstly, volts per hertz control, also known as scalar control, is the simplest and most common control method. It maintains a constant ratio between voltage and frequency to regulate motor speed. While easy to implement, it provides limited torque control and may result in reduced performance at low speeds. Secondly, sensorless vector control improves upon volts per hertz control by estimating the motor's flux and torque without using a speed sensor. It offers better torque performance and speed regulation compared to volts per hertz control, particularly at low speeds. However, its performance is still limited compared to sensor-based vector control. Thirdly, field-oriented control, also known as vector control, provides precise control of motor torque and speed by independently controlling the motor's flux and torque components. It requires feedback from a speed sensor, such as an encoder, to accurately determine the motor's position and speed. Vector control offers excellent dynamic performance and is suitable for demanding applications requiring high precision. Fourthly, direct torque control directly controls the motor's torque and flux by adjusting the inverter's switching patterns. It does not require a speed sensor and offers fast torque response and good low-speed performance. However, it can be more complex to implement compared to other control methods. Fifthly, closed-loop control uses feedback from sensors to precisely regulate motor speed, torque, or position. It offers the highest level of accuracy and control and is suitable for applications requiring tight tolerances. The choice of control method depends on the application's requirements. Volts per Hertz control is suitable for basic applications where precise speed and torque control are not critical. Sensorless vector control provides a good balance of performance and cost for applications requiring improved low-speed performance. Vector control and direct torque control are suitable for demanding applications requiring high precision and dynamic performance. Closed-loop control is used in applications where the highest level of accuracy and control is needed. When operating motors at low frequencies, it's important to consider the impact on motor cooling. Standard induction motors rely on a shaft-mounted fan for cooling, which becomes less effective at low speeds. Therefore, the motor may require additional cooling, such as a separately powered fan, to prevent overheating. Furthermore, the volts per Hertz ratio may need to be adjusted at low frequencies to compensate for the motor's inherent characteristics. Some VFD offer a boost function that increases the voltage at low frequencies to improve starting torque. However, it's important to avoid overfluxing the motor, as this can lead to overheating and damage. In summary, variable frequency drives offer a range of control methods to optimize motor performance for specific applications. The choice of control method depends on the application's requirements, and additional considerations may be necessary when operating motors at low frequencies. Understanding the various aspects of motor control is essential for maximizing efficiency, reliability, and performance in industrial applications. When dealing with induction motors and variable frequency drives, several key parameters and considerations come into play to ensure optimal performance and longevity. Firstly, the base frequency of the motor is a critical parameter. This is the frequency at which the motor is designed to operate at its rated voltage and horsepower. Typically, this is either 50 Hz or 60 Hz, depending on the region. Operating the motor above or below this frequency will affect its performance characteristics. Secondly, the base voltage is the rated voltage of the motor at the base frequency. The variable frequency drive must be capable of supplying this voltage to ensure the motor operates as intended. Mismatched voltage can lead to reduced performance, overheating, or even damage to the motor. Thirdly, the volts per Hertz ratio is a fundamental concept in variable frequency drive control. Maintaining a constant volts per Hertz ratio is crucial for maintaining constant flux in the motor. This ratio is calculated by dividing the base voltage by the base frequency. As the frequency is adjusted, the voltage must also be adjusted proportionally to maintain this ratio. Fourthly, the slip frequency is the difference between the synchronous speed of the motor and the actual rotor speed. It is an important parameter for vector control schemes where precise control of torque and speed is required. Fifthly, the switching frequency of the variable frequency drive refers to the rate at which the insulated gate bipolar transistors, also known as IGBTs, in the drive switch on and off. Higher switching frequencies can reduce harmonic distortion in the motor current, but they also increase switching losses and can lead to overheating of the drive. Sixthly, the acceleration and deceleration rates are important parameters for controlling the motor's speed changes. Gradual acceleration and deceleration can reduce stress in the motor and the driven equipment, while rapid changes can cause excessive torque and potential damage. Seventhly, the current limit setting is a protective feature that limits the maximum current that a variable frequency drive will supply to the motor. This can prevent overloading and protect the motor from damage. Eighthly, the overload protection settings are designed to protect the motor from overheating due to prolonged overload conditions. These settings typically involve monitoring the motor current and temperature and tripping the drive if certain thresholds are exceeded. Ninthly, the motor's thermal capacity and cooling requirements must be considered, especially when operating at low speeds. Standard induction motors rely on a shaft-mounted fan for cooling, which becomes less effective at low speeds. Additional cooling may be required to prevent overheating. Tenthly, harmonic distortion is a common issue with variable frequency drives. The non-sinusoidal currents produced by the drive can introduce harmonics into the power system, which can cause interference with other equipment and reduce overall system efficiency. Harmonic filters may be required to mitigate these effects. In addition to these parameters, it's also important to consider the motor's nameplate information, including its horsepower, speed, and efficiency. This information is essential for properly configuring the variable frequency drive and ensuring optimal performance. Furthermore, regular maintenance and monitoring of the motor and variable frequency drive are crucial for preventing problems and extending their lifespan. This includes checking for loose connections, monitoring motor temperature, and inspecting the drive for signs of wear or damage. By carefully considering these parameters and considerations, you can ensure that induction motors operate efficiently and reliably under variable frequency drive control. When selecting and applying variable frequency drives with induction motors, several best practices should be followed to ensure optimal performance, reliability, and safety. Firstly, proper motor selection is critical. Choose a motor that is specifically designed for variable frequency drive operation, also known as an inverted duty motor. These motors have enhanced insulation and cooling features to withstand the stresses imposed by the variable frequency drive. Secondly, ensure proper motor sizing. Select a motor that is appropriately sized for the load requirements. Oversizing can lead to reduced efficiency and increased costs, while undersizing can result in overheating and premature failure. Thirdly, use appropriate cabling. Use shielded cables to minimize electromagnetic interference and ensure proper grounding. Follow the manufacturer's recommendations for cable size and length. Fourthly, implement proper grounding techniques. Ground the motor, variable frequency drive, and associated equipment according to the manufacturer's instructions and applicable electrical codes. Proper grounding is essential for safety and for minimizing electrical noise. Fifthly, install input and output filters. Install input line reactors or harmonic filters to reduce harmonic distortion on the power system. Install output filters to reduce voltage stress in the motor windings. Sixthly, provide adequate cooling. Ensure that the motor and variable frequency drive have adequate ventilation to prevent overheating. Consider using forced air cooling or liquid cooling for high-power applications or in harsh environments. Seventhly, configure the variable frequency drive correctly. Set the variable frequency drive parameters according to the motor's nameplate information and the application requirements. Pay close attention to voltage, frequency, current limits, and acceleration/deceleration rates. Eighthly, implement proper protection. Use appropriate overcurrent, overload, and short-circuit protection devices to protect the motor and variable frequency drive from damage. Ninthly, perform regular maintenance. Inspect the motor, variable frequency drive, and associated equipment regularly for signs of wear, damage, or loose connections. Clean the equipment and replace any worn or damaged components. Tenthly, monitor motor and variable frequency drive performance. Use a motor monitoring system to track motor temperature, vibration, and other key parameters. Monitor the variable frequency drive's performance to detect any abnormalities or potential problems. In addition to these best practices, it's also important to follow all applicable safety regulations and codes when working with variable frequency drives and induction motors. This includes wearing appropriate personal protective equipment, following lockout/tagout procedures, and ensuring that all electrical work is performed by qualified personnel. By following these best practices, you can maximize the performance, reliability, and safety of variable frequency drive and induction motor systems.